This diagram contrasts two fluid states. On the left, laminar flow is organized in parallel layers. On the right, turbulent flow mixes chaotically. This organized state expresses internal fluid friction, known as viscosity. In a laminar regime, viscous forces completely dominate movement. Because these parallel layers do not mix, the mechanics of how energy is transferred and lost to friction behave entirely differently than in turbulent systems. This absolute viscous dominance allows us to model pipe behavior, using exact mathematics rather than relying on empirical estimations. The Reynolds number represents the competition between inertial momentum and viscous friction. When internal friction is high, the ratio drops. For the APPSC exam, this is a diagnostic trigger. A low Reynolds number guarantees a laminar state without needing additional data. Identifying a Reynolds number under 2000 in a problem prompt immediately signals you to rely entirely on strict, predictable laminar geometry. This isolates the forces inside the pipe. A constant pressure gradient on the end caps pushes against the internal shear stress resisting along the walls. Therefore, according to the force balance equation, shear stress must vary linearly with the radius. This schematic translates that math into a physical profile. We see a linear distribution where shear stress is highest at the pipe wall and drops to exactly 0 at the center axis. Constant pressure drops guarantee a linear shear profile, forming the first step in our causal derivation. Looking at the velocity profile on the same diagram, the fluid touching the stationary pipe wall has a velocity of 0 due to the no-slip condition. Integrating the linear shear stress equation produces an R-squared curve. This means the velocity profile is strictly parabolic. The Hagen-Poiseuille equations show maximum velocity depends on the pressure gradient and radius squared. Thus, the centerline maximum velocity is exactly twice the average velocity. Examiners frequently provide average discharge and ask for centerline velocity. Simply find average velocity, then double it. This 2.0 ratio is the geometric consequence of a circular boundary acting on a parabolic profile. If we change the boundary from a closed circular pipe to the gap between two parallel plates, the mathematics must adapt. For parallel plates, shear stress remains linear and velocity parabolic. But the different three-dimensional volume alters the average, bringing the ratio of maximum to average velocity down to 1.5. Lock in this anchor. Confusing these geometries is a common test mistake. The physical boundary condition is the ultimate dictator of these velocity ratios. The severity of this parabolic profile has a side effect. Using a simple average velocity in kinetic energy equations will yield inaccurate results. This slide provides the specific numerical correction factors required to account for this energy discrepancy in laminar pipe flow. These values are notably high because the laminar parabola is much more severe than the flatter profile seen in turbulent flow. The final equation in the causal chain is the friction factor. Notice that the friction factor relies entirely on the Reynolds number. Examiners will often plant the relative roughness of the pipe in a problem as a decoy. In this regime, viscous dominance completely overwrites surface friction. You can ignore those decoy variables. We can now view the entire laminar framework as a cohesive, interconnected system. This matrix compares the circular pipe and parallel plates side by side, tracking how the profile shapes remain constant while the ratios and friction factors shift. This cheat sheet isolates the core values you need to pull quickly under exam conditions. Recalling these facts relies on tracking the causal cascade. Constant pressure drops create linear shear, which inevitably yields the parabolic velocity and its rigid geometric ratios. Let's apply this framework directly to an APPSC-style problem. The prompt provides three inputs: a fluid density of 981 kilograms per cubic meter, a shear stress of 0.2452, and a velocity gradient of 0.2 per second. We need to find the kinematic viscosity. We apply Newton's law of viscosity. By isolating dynamic viscosity, we find a value of 1.226. For the final step, we divide that dynamic viscosity by the given density. This yields a kinematic viscosity of 1.25 times 10 to the negative third square meters per second. Converting that value to Stokes identifies the final answer, 12.5 Stokes. Following step-by-step logic and tracking units is your most effective tool for dominating the AEE exam.